Hello all, welcome to the lecture. In the last lecture, we got introduced to the concept of polarizability ellipsoids. Let us first consider the shapes of polarizability ellipsoids of more complex molecules. So, in the last lecture, we talked about the polarizability ellipsoid of a diatomic molecule, that is hydrogen. So, now let us consider the non-linear triatomic molecule, which is water. By analogy with the discussion on hydrogen, which we discussed in the last lecture, we might expect the polarizability surface to be composed of two similar ellipsoids, one for each bond. But we must remember that the oscillating electric field which is applied for Raman spectroscopy is usually of the radiation in the visible to ultraviolet range. So, the wavelength, that is lambda, is of the order of 1 micron or 1 micrometer to 10 nanometer. On the other hand, the molecular bonds have the dimensions of around 0.1 nanometer. So, the radiation cannot probe the finer details of bond polarizability. Instead, the radiation can sense the average polarizability So, the radiation can sense the average polarizability in various directions through the molecule. In case of water, the polarizability is found to be different along all three of the major axes of the molecule. So, all the three ellipsoids are also different. So, the ellipsoids in various orientations are shown in this figure. So, for this orientation, we have this ellipsoid. For this different orientation, the ellipsoid looks like this, and if you look from this direction, the ellipsoid looks this way. For symmetric top molecules, for example, CHCl3 or chloroform, they have polarizability ellipsoids rather similar to those of linear molecules, as we can see in this figure. And finally, for spherical top molecules like CCl4 or methane, the polarizability surfaces are spherical, since they are completely isotropic as far as the incident radiation is concerned, and this is shown in this figure. So, now let us move on to vibrational Raman spectroscopy and focus on the Raman activity of vibrations. If a molecule has no symmetry, it is straightforward to decide whether its vibrational modes will be Raman active or inactive. In fact, in this case we can assume that all its modes are Raman active. However, when the molecule has considerable symmetry, it is not always easy to make the decision, since much consideration is needed to understand whether or not the polarizability changes during the vibration. For a diatomic molecule, let us say like hydrogen, one has only one vibrational mode, and that is along the bond axis. Roughly, the polarizability is related to volume. We have seen this in the last lecture, as the polarizability has the dimension of distance cubed, or we can write length cubed. So, length cubed or distance cubed is volume. Thus, a change in volume indicates a change in the polarizability. Thus, during the vibrational motion of a diatomic molecule, the volume changes, and thus the polarizability will change. And so, this vibration is Raman active. For polyatomic molecules, the problem is a bit more complicated. So, let us consider the asymmetric top molecule water. So, we will consider the asymmetric top, that is water. The polarizability ellipsoids of water are shown in this figure. So, there are three fundamental modes: nu 1, which is the symmetric stretching mode; we have nu 2, which is the bending mode; and also we have nu 3, which is the asymmetric stretching mode. So, the equilibrium configuration for all these modes is at the center, and the extreme positions are shown either on the left or on the right, and the shapes of the polarizability ellipsoid for each conformation of each mode are shown in this figure. So, during the symmetric stretch, the molecule as a whole increases or decreases in size. When a bond is stretched, the electrons forming it are less firmly held by the nuclei, and so the bond becomes more polarizable. Thus, the polarizability ellipsoid increases when the bonds stretch and decreases in size or volume when the bonds compress, but an approximately constant shape is maintained. On the other hand, during the bending motion, that is for nu 2, it is the shape of the ellipsoid that changes the most. For large amplitude vibrations, the molecules change from almost linear configuration to that of a diatomic molecule. So, in asymmetric stretch, which we have here, the third one, the bond shape and size remains approximately constant, but the direction of the major axis change remarkably. Thus, all three modes, the nu 1, nu 2 and nu 3, involve changes in polarizability ellipsoid in one form or the other, and thus all these modes are Raman active. So, now let us consider the triatomic molecule. However, we will consider a linear molecule, which is carbon dioxide. The extreme and equilibrium configurations of the three fundamental modes and their polarizability ellipsoids are shown here. So, this is my nu 1, which is the symmetric stretch. This is nu 2, which is bending, and this is nu 3, which is asymmetric stretch. So, for the symmetric stretching mode, the molecule changes during the motion. So, there is a corresponding fluctuation in the size of the ellipsoid, making this mode Raman active. But on the other hand, the other two modes, that is nu 2 and nu 3, are Raman inactive. It might appear that in case of nu 3 or the asymmetric stretch or nu 2, that is bending, the molecule changes shape and so does the ellipsoid. But we need to consider these cases more carefully, and to do this, let us look into the change in polarizability as a function of some displacement coordinate. Displacement coordinate. We will represent this displacement coordinate by xi. So, for the stretching motion, this xi is a measure of the extension. So, whenever the bond is extended, we have a positive xi, and when the bond is compressed, then we will have a negative xi. So, because we are looking into the change in polarizability as a function of xi, we are plotting here xi on the x axis and polarizability, that is alpha, in the y axis. For the bending mode, the xi measures the displacement of the bond angle, that is the OCO bond angle from the equilibrium value. So, the xi is positive and negative, referring to opposite displacement directions. So, going back to the symmetric stretch of carbon dioxide, if the equilibrium value of the polarizability is alpha 0, that means at xi equals 0, the value of polarizability is alpha 0, then alpha increases and decreases when the bonds stretch and contract respectively. This is because, as we have discussed in the previous lecture, the ellipsoid is proportional to 1 by root over alpha. So, when alpha increases, the ellipsoid becomes smaller, and when alpha decreases, the ellipsoid becomes larger. So, this figure shows the change in the shape or the size of the ellipsoid, and these plots show the change of alpha with respect to the displacement coordinate xi. So, we can see that near the equilibrium for the symmetric stretch, the curve has a distinct slope. In other words, we can write d alpha d xi is not equal to 0 at xi equals 0. Thus, for small displacements, the motion produces a change in polarizability, and therefore, this nu 1 is Raman active. Now, if we consider the bending motion or nu 2, we can count a downwards displacement of the oxygen atoms as negative xi, or so this is my negative xi, or the upward displacement of the oxygen atom as positive xi. So, this is the case where I have the upward displacement. So, this is the case of my positive xi. So, this figure shows the change in polarizability, and we can see the change in polarizability is exactly the same for both the positive and negative psi. So, now we can say d alpha d psi at psi equals 0 equals 0, and hence for small displacements there is effectively no change in the polarizability and the motion is Raman inactive. Same argument applies for this nu 3 or the asymmetric stretch. Here the polarizability decreases for positive and negative displacement coordinate. So, again we can write d alpha d psi at psi equals 0 is 0. So, for small displacements there is no change in polarizability, and again nu 3 or asymmetric stretching mode of CO2 is Raman inactive. So, for a mode to be Raman active, in general we need to have d alpha d psi, this needs to be non-zero at psi equals to 0. In general, however, the slope, that is d alpha d psi, would have different values at the equilibrium position. Since we have seen that Raman spectrum is forbidden when d alpha d psi equals 0 and allowed for d alpha d psi not equals 0. So, this is my allowed case and this is my forbidden case. So, we can imagine that the degree of allowedness varies with the value of the slope, that is d alpha d psi. Thus, if the polarizability curve has a large slope at the equilibrium position, the Raman line will be strong, and if the slope is small, then the Raman line will be weak. For example, for the symmetric vibrations, these vibrations give rise to intense Raman lines. On the other hand, the non-symmetric ones are usually weak and sometimes unobservable. In particular, a bending motion generally yields a very weak Raman line. So, let us look into the Raman and IR activities of the different modes of CO2. So, for CO2 we have these different modes. We have nu 1 which is symmetric, we have nu 2 which is the bending mode, and nu 3 which is the asymmetric stretch. So, nu 1 is symmetric stretch, and now we have already seen IR that the nu 1 is IR inactive and nu 2 and nu 3 are IR active. And today we have seen in case of Raman spectroscopy, nu 1 is Raman active and nu 2 and nu 3 are Raman inactive. So, it can be seen that the modes which are IR active are Raman inactive and vice versa. That the IR active modes are Raman inactive and vice versa is a general rule valid for all centrosymmetric molecules, and we can see this carbon dioxide which is C double bond O double bond O. So, C is the central atom, this is a centrosymmetric molecule or a molecule which has an inversion symmetry. So, for centrosymmetric molecules, this rule is valid, that if it is IR active, it will be Raman inactive and vice versa, and this rule is the rule of mutual exclusion. So, if there is no center of symmetry, then most vibrations are both IR and Raman active. So, there is, in that case there will be no rule of mutual exclusion. The converse of this rule, that is the rule of mutual exclusion, is also true, that is the observance of Raman and IR spectra showing no common lines implies that the molecule has a center of symmetry. However, just a note of caution, as we have already discussed, a vibration may be Raman active, but too weak to be observed. However, if some vibrations are observed to give coincident Raman and IR absorptions, then it is certain that the molecule has no center of symmetry. So, now let us take one more example. Let us think about the molecule which is a triatomic molecule, that is N2O. And if we do not know the structure, we can think that there can be two possible structures. In one case, I can write the sequence as N, N and O, and in the second case, I can write as N, O and N. So, if the structure is one, that is N, N and O, then there is no inversion center for this linear molecule. Thus, the mutual exclusion principle will not be valid. So, if the structure is 1, there will be no rule of mutual exclusion. So, all the modes will be Raman as well as IR active. On the other hand, if the actual structure is NON, then it is a linear molecule, but it is also a centrosymmetric molecule. So, we can think this molecule as something similar to CO2 or carbon dioxide. Thus, it will conform to mutual exclusion rule. So, if it is NON, then this mutual exclusion rule will be valid. So, all the modes will not be IR and Raman active. In other words, the IR active vibrations will be Raman inactive and the Raman active vibrations will be IR inactive. So, from experiment, it has been found that all the vibrational modes of this molecule N2O are both IR and Raman active. So, this result along with the rule of mutual exclusion tells us that the structure of N2O is 1, that is NNO, and not 2, that is NON. In other words, N2O is not centrosymmetric.